So hello everyone, welcome to the Generative Programmatic Solution tutorial. And we are very excited to talk about some Programmatic RL and code generation stuff. My name is Xiaohua Sang. I'm a faculty at National Taiwan University. And the two other organizers are Lepi, a faculty at University of Alberta, and Xingwing, a staff research scientist at Google DeepMind. So here's our schedule for today. Lepi and I will talk about Programmatic RL from two different perspectives, and Xing will talk about code generation. So we will have Q&A session at the end of each talk, and so we debated a lot if we should have break in between, but then we realized there's like so much that we're going to talk about, so we probably wouldn't have official break, but you can take break as needed. Okay, so I will start with my part. I will talk about learning to synthesize program as interpretable and generalizable RL policies. So let's first talk about Deep RL. So Deep RL has been very, very powerful in many domains like RBOT code, RBOT start and stop. And if you think about what Deep RL really is it's about the agent and policy in an environment. And the environment has a state where like this maze navigation kind of tells you have an agent in this maze and then you want to navigate. And the policy and agent can observe the environment to get an observation. And given this observation, we want to be able to look at what kind of action we can take and taking actions. And because this agent is in this environment, right? So the agent in turn affect what the state of the environment. So the environment transition to next state. And also environment provide a signal reward and telling the policy like how well you're doing. And the goal of RL is to maximize the total reward, which is also called returned. And this formulation has been very, very powerful. It can solve like many sequential decision-making kind of problems. But in this talk, what I want to talk about is actually the issues of Deep RL formulations. One very important issue of Deep RL is about generalizations. So if you think about what Deep RL really is doing, it's about having a deep neural network representing a policies, right? And you could train this neural network to do navigation in different size of maze, different layout of maze, different start and go locations. And once you train that, you get a policy. So this policy know how to navigate in different kind of maze. So you must like know the underlying rule of the maze navigation, the right-hand rules. Does anybody know like the right-hand rules, like in maze navigation? Can you raise your hand if you know the right-hand rules? Oh, great, there are many. Okay, so for those who don't know, the right-hand rule is about like if you get stuck in the maze, in case like somehow, like hopefully not, then you can put your right hand on the wall. And you can just like keep sticking your right hand on the wall and just like go all the way through the maze. Then you can get to the exit. So that's like right hand rule. So don't get stuck in the maze, but if you do, remember this right hand rules. So now you have this policy like in different side of maze with different layout, you can navigate. So it must learn right hand rule. But then when we turn this like trend policy into like a larger maze, it doesn't work. So that's what we tried. It just doesn't work. It's just like this deep neural network somehow find a really weird way to memorize like how to solve navigation, but it does not generalize beyond the scope of the task. So that's one issue. And you don't want a robot policy that does not generalize, feel like miserably like at your home, right? So generalization is one issue. And another important issue is interpretability. So when you have a neural network policy, it's very hard to understand what this policy thinks, right? So it just map a state to an actions, but you don't know what this network is thinking. You don't know what it's going to do next, what's going to do after, and what the decision-making logic of this policy. Just you don't know because this is a black box. And we don't want this black box policy, especially in say robot learning or this like safety critical kind of task. You want the policy that you understand. You want to understand the decision-making logic. So that's the problem of deep neural networks as a policy. So instead, there are some people in this like broader field of like RL. They work on a topic I call programmatic RL. So the motivation is about like, can we have a policy that is more generalizable and more interpretable? That's like the whole idea. So what this kind of works like, they do like, hey, we pick a representation that is more structured or better in terms of interpretability or generalization. And then say, hey, we also develop methods that could learn such a policy from reward. So some examples are like decision tree. So decision tree is like prior to neural network. It's like more traditional machine learning kind of model, which is like more understandable to humans. Or we could do this like language description kind of policy where it describe what to do first, what to do next, and what to do if that condition is satisfied or not. And also some people are doing like symbolic kind of program where you learn a parameter program and then you can run the programs. Or like some state machine policy where you have multiple mode, you can transition between different mode and different mode represent different macro actions. So those are some programmatic RL example where the whole goal is about, can we not do deep neural network as a policy? Because this is just like not so readable to human, not generalizable. Can we do better? Can we have more structured representation? So this is programmatic RL, like in my definitions. So this work Viper, they like Neurips 2018 paper, they did this like decision tree policy. And the whole idea is about like, can we have policy more interpretable and more verifiable? So what they do is like, hey, given the task, we first train a neural network policy, and we mark this neural network as an oracle, and then we try to distill what this neural network would do in different situations. So this is more like imitation learning kind of method where we have a decision tree that distilled what neural network policy has learned. So this Viper algorithm. And the whole point of this is about, can we have a policy that I can verify in the sense that I know how much perturbation I add to the state, I will get you the same actions. And this gives you this guarantee, like you know the margin, because now we are having a decision tree policy. But one thing to know that is, given this like decision tree, you actually need to handcrafted state feature, so that you could learn this decision tree. But it's a lot more interpretable than deep neural network policy. And there is another work, Propel is like about a symbolic program kind of policy. And the nice idea of this work is about when you want to distill a neural network oracle, you probably shouldn't do this at the very end. So like Viper, you train a neural network and it get to maximize the return, and then you distill the network. But you don't think about this distillation while you train the neural network policy. And this might not work well. So what this paper is proposing is that while training this neural network policy, you should also think about where you want to project this policy. So when you want to project this policy into a symbolic representation, then you probably should regularize this neural network policy somehow so that the projection doesn't just lose too much information. So this is the idea of this Propel paper. And they're showing this like racing track kind of environment where this way, like the symbolic program could be more generalizable to different tracks. And another type of policy that I want to mention here is state machine policy, where you have this like finite state machine kind of policy. You could have a set of mode of different macro actions, and then you learn to, once you extract a set of macro action, then you learn transition between different kind of mode. And this paper showed interesting things about like this like parallel parking. Like if you like know how to park a car, then you know this like parallel parking kind of problem. And they show that by learning the state machine policy, you could generalize to even harder problem than whatever tag you have seen in your training example. And they show this like in different kind of domain, and it's very interesting. And they call this like inductive generalizations. So far we talked about like all this kind of different representation policy. And I want to focus on in this talk is about this DSL policy, where you want to describe program using programming language. And the whole idea of doing this is, first, like this is a lot more interpretable than decision tree. Like you couldn't read decision tree, but now if you have a policy represented in programming language, you could read it as long as you know some basic programming skill. As long as you know like some control flow, like if else, or you like while loop, like you could read a program policy. So this is like human interpretable, and also it's executable. Like once you have this like DSL defined, like domain specific language, then you could also have this compiler that could run these programs. And hopefully by having this like nice structure, it could be more generalizable. Just imagine when you were learning introduction to programming course, like when you program like addition programs, then you could just do the addition program in like maybe 3 to 5 digits. But once your program is bug free, it can generalize to like 100,000 digit addition problems. And we also want this program to have this nice generalization because of this structure. Like this structured search space could be nicer to represent the policy. So in the following, I will talk about a series of work that try to represent policy using language programs and see how well it can do in terms of generalization and different kind of tasks. So the first work I want to talk about is neural programming synthesis from demonstration video kind of stuff. So if you think about this like subset of RL problem like imitation learning, given demonstration, you want to learn a policy that can mimic the expert behavior. What people normally do would be like, say, can I just learn new neural policy and that can mimic the this expert behavior in different kind of situations. And in this work, what we want to do is like, can we instead, given demonstration, we want to write a program that explicitly tell you about the decision-making logic of this expert. And once we have this program, because this program is executable, right? So in different situations, I could just execute this program and then get to mimic the behavior of the experts. So that's what we want to do in this project. So we just, in this two domain, we create a bunch of different programs, and then we execute the program to get the demonstrations. And we can split it like training, validation, testing set, and we can use the training set to learn this like demonstration to program kind of mapping. So if you come back to this like imitation learning with new neural policy, what I do is like given demonstration, you learn new neural policy, they could learn this state to action mapping, and given some validation initial state, then we could just like roll out a policy to get a predicted executions. Then we can compare this to the ground truth executions. And then this is how we evaluate how this policy is learning. And in our situation is we want to actually write a program. So given a training program, we could just make a network to given a demonstration to predict a sequence of tokens, and we can compute the loss between the ground truth program and its predicted programs. Then when we evaluate, we want to know how well this policy can mimic the experts. Then we can run the program and get a predicted executions. Then we can compute the loss, compute the accuracy or loss, some kind of loss with ground truth executions. So this is how we train and evaluate. So now the predicted target is no longer state to action, but it's about demonstration to programs. So we compare this like two ways of representing policy, the program and the neural networks. And we show like in different domains, actually using the program to represent policy get you much better performance. And when looking to the qualitative result is that why is this happening? Like why is program better? What we found is that say given a demonstration that you have this like underlying program to have like if else branch, and when you have demonstration like this where you have like many other program go to if branch and there's only one single demonstration going to else branch, then when you have a neural network as a policy, it will just learn this very general tendency to move, because like many of demonstrations just do move. And once you just go for move, then you get a very low loss. So it will just miss the minor branch. But when you have your policy to be a program, when you do this like learning, you force the policy, the network to actually realize what's going on, what this expert is doing, because if it's missed the else branch, it gets penalized a lot. So by making this network to do a much harder job, not just state to action mapping, you actually force the network to actually learn what this expert is thinking. And that's like the interesting finding of this work. So in this work, we talk about this, how you can go from demonstration to program. And this program is a nice representation of policy. But in many cases, in RL, you don't have demonstration. You just have reward. So can we just, given reward, we could get the program policy without any demonstration is what we're going to do next. So unlike deep RL, where we have neural networks and we can just execute a neural network to do this bunch of state action and then collect them and collect reward and do the learning, what we want to do is we want to represent the policy as a program again. And when we want to do the rollout, want to do the execution, we just execute the program given the compiler. So now the problem becomes, can we have a model that can write programs? And once you write the program and execute the program, you get a reward. Then can we improve this program? So that's what we want to do in this project. So given just reward signal, we want to have a program that could be executed and maximize the return. So we proposed a framework that we call LLMs. And to get a model that could write program and that can maximize return, it's very hard. So it needs to understand the program grammar, like the programming language grammar. It needs to understand the environment dynamic, like how this program will execute, what will be the execution traces of this program. And also you need to understand the task, like what this task is about. How can I maximize the return? That's very hard. So we try to make this hard problem into two steps. So in first step, we don't even think about the task. We just think about how I can learn the grammar, how I can learn the environment dynamics. So what we do is we just randomly generate bunch of programs. Like they are not test related at all. They're just a random program. And given a grammar, we could sample a bunch of random programs. So we sample many programs that are not related to task. And then we just learn an autoencoder that could encode program into latent space and then decode the program back. And we could just maximize this reconstruction loss. And also we have some regularization term that try to make this embedding smooth in terms of behavior so that the closer program behave similarly and program that are farther away have different behavior. So you could spin embedding space that when you sample the vector from this embedding space that represent different kind of behavior. So that's what we do first. So it's consider the program grammar. Now the decoder could decode grammatically correct program. And also we consider the behavior and also how the program executes in the environment. But now we haven't talked about a task. Like we don't even understand what this task is about, but just learn the entire embedding space based on the grammar and environment dynamics. Then now given the task that we really want to solve, so what we do is very simple. We just search in the embedding space. So we could sample a bunch of program candidates in this embedding space. And this embedding vector could be decoded into programs, right? Because we have learned this decoder. And once you decode it into a program, then you could execute the program, and then you could get a return of this program. And this is your fitness score in searching. So we do this cross entropy method to keep searching in this embedding space until we find a good program that could be decoded and maximize the return. And we say, hey, we're done. This is our program policy. So that's what we did for this entire framework. We learned embedding space, and we search in embedding space, and because we are able to decode the program, so now you have a program policy that works. So we have evaluated this framework in a bunch of different algorithmic tasks like this. And we have shown that with compared to DRL, we could solve tasks with like sparse reward. And also we visualize the search moving, whereas like in the embedding space, like the whole search population is getting closer and closer to the program with ground truth behavior. And we can solve a bunch of tasks compared to like some other algorithm. But this is not as exciting. This is just like very toy example, right? So we just like, you could solve some task and that's it. What really excited us is about generalization and also interpretability. So we tried this, just like the maze example that we talked about. So given like the A by A maze environment, we synthesize the policy, the program policy with the LLM framework. Then we just put this LLM generated program into much larger environment, but like it's still about navigation, and it does work. And if you look closely, this program actually learned this right-hand rule. So this is the navigation program. It could be run in any kind of navigation problem. It could solve the navigation problem. So this program is actually the solution. So it's not just like deep neural where you try to memorize whatever training example that you have seen. Just based on this A by A maze example, now you have a policy that could do navigation in whatever kind of environment. And this generalization is exactly what we want, and that's exactly what we're hoping for when you are developing a programmatic space for policies. So we also show this like quantitative result where we have generalization ability a lot better than deep RL, and also decision tree policy. So that's about generalizations. And about interpretability, like what interesting thing is where we give some suboptimal program synthesized by our method, and we call like some undergrad to fix the programs. Like we're just like hiring them, hey, can you do some like 3 to 5 program token editing, and can you improve the policy? And it turns out that like people with programming skills, they could improve this policy. And when you have deep neural policy, there's almost impossible to hire someone to, hey, can you debug this neural policy? Can you change the weight and bias of this neural network and improve the performance? But now you have a program policy. This is interpretable, like people could understand, could improve them. So this is very exciting. Now you could, with this interpretability, you not just only understand, now you could fix the program. And that's a finding from this framework. And another work I want to talk about is like following up this LLM project where we know having program as a policy, purely learning from reward is possible. But still it has some problem. One problem it has is about this limited distribution problem. So in LLMs, the way we spend this program embedding space is we randomly generate a bunch of programs, right? And that training data set actually limited the distribution of programs. So imagine now you have like all the data set with like less than 100 lines of programs. Then given the testing test that you want the program or the model to run is like say require 1,000 lines of code. And this decoder will never decode like 1,000 line of code. So it limited distribution by the training on the data set. And another problem is the credit assignment issue, where when we do the search, you execute the entire program and you get one single score. But this environment tells you a lot more. Like you get reward along the way. But when you evaluate using the search method, you just like sum up all the reward. And this is just like not as detailed. So what we want to do is like you want to know which part of the program actually does well, which part of the program does not do well, and you want to improve that part that don't do well, right? So that doesn't happen in Lips, like we just consider entire score. So in this project, we call Hierarchical Programmatic RL. We want to fix this two things. So we're still learning embedding space. But then what we do is like we don't do search in this embedding space anymore. What we do is that we learn a policy that given the state and try to consider this program embedding space as its action space. And then we do RL. So we can take an action in this embedding space, and then this action program latent could be decoded into a program segment, a subprograms. And then we could execute the program and get the next state. And also get the reward you get along executing this small picks of program. And the policy would pick another actions, just like RL. Now you are taking the second action, which this action, again, is a program latence, and then you can decode this. And then once you decode that, you can then execute this second program segments, and you also get a reward. And you could do this like all the way, just like how you run RL. You sequentially make sequence of actions, and then you get the next state and the reward. And just like RL, what we want to do is we maximize the total return. So now we turn this back into, again, an RL problem. But now the R problem is about finding a program policy. And then the program put together is this composed program is our program policies. And by doing so, we show that in all the tasks on the task that proposed in Lips, this HPR actually does better. So we try to create another set of tasks that are harder. And we also show that our method actually work a lot better than the prior method in this like harder task. But this is just like the task performance. So we really want to verify if this performance gain comes from fix this like limit distribution problem and also the credit assignment issue. So we try to run like the testing test to be longer and longer. And we show that Lips actually cannot generate longer programs, but HPR could. And also we try to see if rewarding the entire program at the very end or try to give denser reward by doing this like step action reward kind of formulation will make the performance better. Like you could converge faster, you could converge better policies. So that the HPR framework. And a work I want to quickly talk about is the work that we're going to present this Neurips at the poster session is fixing the problem of this, again, the HPR problem. So that HPR problem is about we treated this program embedding space as action space and you do RL. But this action embedding space is very, very large. So it's like 256 dimensional. So with this like large action space, it's very hard to train a policy. So it takes like almost a week to train this framework on some hard task. So could we actually make this a lot more efficient? And this Hippo exactly does that. So we try to first separate this into two stages. In first stage, we try to first retrieve a set of program segments that are like very diverse and they are effective getting some reward from some part of task. And also they could be composed together. And then we can learn the high level policy to just use this a finite set of options and this learn a lot faster. And we show that this could do a lot faster in many other tasks. And this will be in the poster session 5 this Friday. So if you are interested in like learning programmatic RL, you could talk to Zhihan and Guanting, which are also here, and me at the poster sessions. And the final work I want to mention about this like programmatic policy stuff is about how we use LM to actually accelerate the entire process. So now we know like many work that does this programmatic RL, like generate a program policy by doing search or like RL, this kind of different optimization method. So this kind of method, they are nice because they are directly optimizing the objective, but they are also not as nice because they are assumption free. They assume nothing about the task. But in this kind of like algorithmatic task, we actually do know a lot more. Like we know what kind of problem humans are interested in. Like we we're not interested in like randomly generated tasks. Like there are some goal-directed behavior that we care about, but this method, like they don't know. They just like, they do whatever search optimization to get a policy. And on the other hand, you have this LLM, where you could imagine LLMs like this, like knowledge base is like a clone of human civilization on the internet. So they know a lot about what humans are interested in, but also they are very hard to directly optimize for some return, because like those networks, like say GPT, like you couldn't even fine tune the model. So they have this like knowledge and also programming skill, but it's very hard to directly optimize them. On the other hand, you have some search method or optimization method or RL where you could optimize some objective directly, but they just like know nothing about this word. So in this project, we try to combine them. We propose a method called LLM guided search, where you first generate an initial search distribution of program by prompting LLMs, and start from there. You do the search to improve the programs. And that could actually get you a lot more simple efficient, where you could do a lot fewer human execution, program execution in the environment, and you can get a really good performance. And we also show how you combine different search method with LLM and with like different kind of setting, it works well. And also we want to highlight one example where it's like, could LLM actually continually improve the programs without any search method? So we try different way to let the LLM know like how the program is generate does. So we try to provide reward, try to provide execution traces, and try to make the LLM to improve the program. And the conclusion is actually that so LLM could very quickly saturate. So it does not know well about the environment, does not know what's going on, so it could not keep improving the program. But the search method could. And that's kind of our conclusion from this project. So we quickly go through all this work that try to do program policy from reward from demonstrations. And I just want you guys to have this takeaway, which is combining program synthesis and RL could get you more interpretable and generalizable kind of policy. And that is only one dimension. Now we are using program to represent a policy. And there are also some interesting work that use code as policy to do some robot learning kind of tests. They are also very interesting. And there are some other dimensions that we could also use programs. One exciting direction will be use codes to as a reward function, where you generate reward function code through train model to do different kind of tasks. And like this Hierarchical and also language to reward. And also another way you could use program for this agent learning will be you could generate code for programmatically generate different kind of tasks, and you train the model. And also another way to do this like program will be you use program as models. So there's like code word model where you try to do model-based R kind of stuff. You try to have a model to write a code for you, and this code will roll out. And you could just do this imaginary rollout, and you don't need to interact with the environment. And there's also another exciting direction. So there are just many directions that you could do programs to improve this like agent learning, improve RL, and they're just very exciting that you could take a look. So with that, that's kind of what I want to share today. And sorry, it's a bit rushed because of some technical issue. And I put all the reference here. And also I will put my slide with my personal web page. And also here, you can just scan the QR code as well. So we could do maybe 2 to 3 minute questions. Then I will give the stage to Luffy. Any questions? Yes, please.
Yeah, I was wondering about the quality of the embedding space. So it seems that for this type of methods to work, the embedding space should be kind of smooth. I mean, basically the reward function should be kind of smooth in the embedding space. How can you build the embedding space such that it has these properties?
Right. So in the LIPS paper, so that's very important. So if you just do reconstruction, the program just like in this embedding space, like scatter around, like they don't make sense. So we have this like regularization term where there are 2 levels of regularization. So one is we have another policy that decode embeddings and try to follow the behavior of the program. And we could maximize the ground truth program action sequences and also the neural network decode policy action sequence, try to bring them close together. And also another way to regularize this is given the decode programs, you can execute the decoder program and you get the predicted action sequences. You could also try to bring this closer, and because this like execution is not differentiable, you could do RL to then regularize the embedding space. So we have some regularization that try to make the two programs that have the same behavior to be closer in the embedding space, and that's very important.
I have a question. So this idea is pretty cool. I'm wondering how complex is the program that the model generates?
Yeah, so the program at this stage is like not complex at all. Like they at most like less than 100 line of tokens. So they are very toyish at this point.
Okay, thank you.
Thanks. Yes, please.
I was very fascinated about your idea to have your model generate a prompt for an LLM, but it feels kind of wasteful to create like a text prompt and run it through a tokenizer. Could you just directly create tokens instead of a text prompt?
Right. So we just like write a description about the domain and the task, and then we just prompt the GPT. So like hopefully it understand how this domain is working and what this task is about. Right. So that's what we did.
Okay. Thanks.
Thank you.
I have one more question.
Okay.
Just one.
Yeah.
So the manifold that you learn in the latent space, it has to be wide enough to contain the optimal trajectory. How can you guarantee that you trained enough trajectories that contain the good one? And also, how do you optimize the walk through the manifold that yields the optimum?
Yeah, thanks a lot. So, right. So there's no guarantee. So what we do was just like we create a randomly programmed data set that try to contain like many programs. But many of these programs are actually not as useful. So like the whole idea is like you still need to do some search or RL in this like large space and try to find some useful program to your task. But there's just like no guarantee.
All right. So my name is Levi. Thank you, Xiaohua. This was a very nice introduction to programmatic reinforcement learning. And maybe before we get deep into the topic again, I just want to take a step back and try to digest some of the really cool ideas that Xiaohua presented here today. So I want to start with this claim that deep reinforcement learning is programmatic reinforcement learning. And the reason why this is the case is actually very simple. So what Xiaohua was showing us is that you have this reinforcement learning problem. You want to try to find a policy to solve this problem. And what we do is that we're going to define the language in which we're going to search over and try to find a solution to the problem. So if you look at deep reinforcement learning, maybe we can have this cartoonish perspective where we're looking for all possible policies that you can attain with a neural network. So you're going to sit down, you're going to write down the architecture of the neural network, and then you're going to train that neural network with gradient descent. And what you get as output is your policy. But then if you take a step back and you consider that you have the power of actually choosing the language, then we're going to have something that looks like this. So instead of always choosing, let's say, a neural network to represent the policies, I could choose something else. So I can choose, for example, the RL language that Xiaohua had for some of the examples that he showed here today. And I think this is very important because it allows us to go back and choose the right biases that we need in order to solve the reinforcement learning problem that we're interested in solving. Like, for example, if we take bees, then bees, they actually can learn somewhat quickly how to differentiate the painting style of different artists and which kind of bias that's going on in the bees' brains. So this is the kind of biases that we might be able to go back and try to understand what we need so that we choose the right language. And then once we have the right language, we can try to solve the problems that we're interested in solving. So Xiaohua focused really on generalization and being able to understand what's going on. I want to add a new dimension. And this new dimension is going to be throughout my part of the talk, of the tutorial here today, which is the ability of combining these programs. So once we learn how to solve a problem, then we might be able to get different pieces of the solution and combine them into bigger solutions and discover new stuff that way. Okay, so that's going to be the common theme. And we're going to keep in mind that deep reinforcement learning is going to be a subset of programmatic reinforcement learning, given this perspective that I'm giving to you right now. Okay. So search for programmatic policies. So what do we need then, given that we have a reinforcement learning problem and we're interested in solving this problem? So first of all, we need to define what is the search space. So once we define the search space, we're saying here's a family of policies that are going to be searching over and are going to try to find a policy within this space that's going to maximize return. I also need to define what is the search procedure. So once I define the search space, how am I going to go about the search space and try to find a policy that I'm looking for? And if you look at the deep reinforcement learning approach, what we have is that the search space is the weight of a neural network. Because what we do in practice is that we're going to sit down and we're going to write what is the architecture that we're going to use with our deep reinforcement learning agent. And once we do so, now we have defined our space. And we're going to search over the space so that we can find the right set of weights so that the agent is going to have the behavior that will maximize return. And what is the search procedure? Well, the search procedure is going to be gradient based. So we're going to do gradient ascent so that we can maximize return. And that's what we do in deep reinforcement learning. So in taking our step back and trying to find a more general solution to this problem, we're going to change both the search space and the search procedure as well. Okay. So let me give a very concrete example. So this is a tutorial. I'm going to give you something very simple so that you can understand what's going on. And maybe you're going to be able to sit down and implement yourself this more general version of solving reinforcement learning problems. So we're going to start by defining the search space. And in order to define the search space, we're going to define a programming language. So the programming language will define what we can search over. And we're going to do this with a context-free grammar. So here we have the initial symbol, this capital S in the first line, and we can transform this capital S by one of the production rules that we have on the right-hand side. Like, for example, we could transform the capital S into this if-then-else statement, which is the last production rule that we have on the right-hand side. We also have this capital B letter, which is also what we call a non-terminal symbol, which we can replace with one of the production rules that we have at the bottom. So then this language essentially allows you to do addition, and you have a few if-then-else's check in order to write these programs. So let me just make sure everybody's still paying attention. I'm going to ask a little quiz. So what about this program? If x less or equal than y, then 0 else 1. Can we actually write this program in the language that we have above? So the answer should be yes. We can do this, and I'm going to show you the production rules that we need to apply in order to start with the initial symbol S and get all the way to the program that we're showing here. So we're going to start with the symbol S, and then we replace it with the if then else, and then we can replace each one of these non-terminal symbols so that we get all the way to the bottom to this program. So this is a program, we say that it is accepted by this language. And every program that we can write in this language, that's going to define the space of policies that we can search over. So that's how we're defining the problem. And as you can guess from looking into this, and if you're familiar with deep reinforcement learning, the big assumption that we make with deep reinforcement learning is that the search space is going to be fully differentiable, which is super nice. Like now we can train this end to end and have our policies. But here now I have the space that's possibly discontinuous, and I can't just, plug and play graded descent and get to solve this problem. So I need something different. And I'm going to tell you one example of how we can make this happen. Before we do so, before we go into the search part, how we're going to go about the space and find a solution, let me just tell you how we're going to represent this in memory. So how do we represent a program in memory? And this is almost like giving you the implementation. If you want to sit down and implement this, you need to implement this tree, which we call the syntax abstract tree. And it's essentially representing the entire program. You can see the production rules within the tree. You look at the root of the tree, it has the initial symbol capital S. And then in the first layer, it's applying the first production rule where we're replacing a capital S with the if then else. And then we're going to keep going like this so that in the leaf nodes of the tree, we have what we call the non-terminals or the terminal symbols of the language, pardon me, which is given the program that we have in blue at the top. So if you just traverse the leaf nodes, you're going to recover exactly the program. So that's how we're going to represent this in memory. It's also a very convenient way if you want to implement an interpreter so that you can go about this tree and you can run this program in memory. Okay. So that's how we represent in memory, how we define the space is through this language. Then the question is, how are we going to search in this space? So in order to search over this space, we're going to define what we call a neighborhood function, because we're going to be using some local search algorithm. So if you're familiar with the introductory courses in AI, you might remember hill climbing, this kind of local search, which is also very similar to what Xiaohua was talking about when we're doing local search and the latent space. So let's define a neighborhood function. A neighborhood function is going to take what we call a candidate solution, which is essentially a program that's a candidate to be in the policy that we're looking for so that we can maximize return. And what we're going to do is that we're going to do a little mutation in this tree so that we can get a neighbor. We're going to randomly choose a subtree. Let's say that we choose the subtree here, and we're going to replace this with something else. And the something else, we can go back to the language and ask it to generate something for us so that we can generate the whole tree, the whole subtree, and get something different. So what we're doing here is that we'll replace that subtree with something else. And there are some important properties going on here. So the idea that the program that we have on the right-hand side being a neighbor of the program on the left-hand side is that the program on the right-hand side is similar to the one on the left-hand side, and yet it's doing something different. So this is going to be important later as we discuss how we try to learn spaces that are friendly to search algorithms. Okay, so if I do this, let's say k times, I'm going to have k neighbors, and then I can evaluate all these k neighbors, and then the search algorithm will define us what we're going to do next. So how can we search over this space? I want to keep this as simple as possible. So I want to have an algorithm that as simple as graded descent, but now to this more general problem where we cannot make the assumption that everything is going to be fully differentiable. So this is going to be hill climbing. So the way that we're going to do hill climbing is to first generate a random candidate solution, and that can be done by just applying the production rules that we have in the language. So let's say that the program that I showed you before in my little quiz is actually a program that we generated at random. So we're just applying all these different production rules so that we get to the point where all the symbols that we have in this program, they're actually terminal symbols. So then I'm going to just use this little circle that you see at the bottom. That's going to represent that program. And this oval shape is just representing the entire state space or the entire program space that we're going to search over. So we're going to move that little symbol all the way to the oval space. And we're going to use our neighborhood function. So let's say that we query the neighborhood function. We get a bunch of neighbors. And now we're going to evaluate each one of these neighbors. If we're solving a reinforcement learning problem, then each one of these neighbors, they're going to represent a policy, and we're going to roll out that policy, and we're going to get something back. So we look at all of them, and then the best one is just going to blink. I believe it's blinking somewhere. There you go. So then that's the best one, and that's where we're going to jump. So we're going to be super greedy. That's the idea of hill climbing search. And then we generate the neighbors again, and we jump to the best one, and we generate its neighbors, and we're going to continue like this until we get to the point where the current candidate solution that we have is actually better than all the neighbors. So this is the hill climbing approach, and that's where we're going to stop. We just reached this local optimum, and that's the solution that hill climbing is going to return to us. Very similar to how we would do with graded ascent, except that now we don't have graded information. We're sitting in this more general space where you could have programs that are actually discontinuous. Okay, but what do we do with this? So in Intro to AI, we should teach people that we should do restarts, and restarts. So if you're doing local search, then these local searches, they tend to be very fast, but we can run many of them. So then if I run the search again, I'm going to start from a different initial candidate solution. I'm probably going to be in the different part of the space, and I'm going to run the search again. And I do it again and again and again. And once I run out of time, then I can look at all the solutions that I encounter, and I can return the best one. And this is also a cool solution in the sense that's very easy to parallelize. I can run one search in each core, and I can get many searches going at the same time. And this is very powerful. All right. So I gave you a very concrete example of how you could go about solving reinforcement learning problems with this more general framework. So we're going to take a step back and say, I'm not going to use only neural networks as my language. I'm going to choose the language so that I can choose the right biases, and that's going to help me solve whichever problem that I want to solve. Okay, so let's go back to the slide that I had before, where we need to define the search space and the search procedure. You might remember that for deep reinforcement learning, we had the weights of the neural network as the space and graded ascent as the search algorithm. But now I still want to keep things very simple. And what I'm going to use is this local search, like hill climbing search, or something similar to this, like the cross-entropy method that Xiaohua explained in his part of the talk as well. So that's the kind of search that we're going to use. And then I think that the interesting questions are around how do we define the search space so that we can make it friendly to this type of search algorithm, so that we can make use of all the cores that we have access to, and we can run many searches in parallel and be successful in finding a solution to these problems. So then I'm going to go through again from a slightly different perspective on the leaps approach that Xiaohua explained. So I realized that my perspective is a little bit different from the one he has. So the paper he explained, he's a co-author. I'm not involved in that paper, but I absolutely love that work. And I studied the paper so much that I feel like it's my own paper. So I can explain it to you as if I had written the paper. So I'm going to go through that again because it's going to be important for our next steps. And the next steps is going to be something related to learning semantic spaces. So this is how we're going to make the search space more friendly so that we can find our policies that we're looking for more quickly. And finally, if you're looking at all of this and say, hey, I don't care about all this discrete search. I like my end-to-end approach. So sit tight. I'm going to show you how we can actually do this end-to-end, and looking at these policies from a programmatic perspective, like seeing the neural networks as programs, can actually be super helpful. And I'm going to show you how we can actually learn options in reinforcement learning by taking this programmatic approach. Okay, so this is more or less the roadmap that I have to the end of my part of the presentation. I'm going to go through the leaps, and then to semantic spaces, and finally how to decompose neural networks to learn options. All right, let's move on. So this is the leaps approach. And what we're trying to do here is really to try to learn a space, in this case, a latent space that's friendly to search algorithms. And this is absolutely the dream. Like, I don't have to deal with this discrete and nasty space given by a programming language. I'm going to learn ahead of time a latent space that's going to make my life so much easier. And they do it in a very clever way. So they're going to learn this autoencoder where this vector Z that you see here in the middle, that's going to be the space defining where we're going to search for our policies. So there's a usual reconstruction loss. So here's a program that are going to provide us input. I'm going to learn how to reconstruct this program. And that's nice. It's training the autoencoder, but it's not enough. So then they came up with two other losses. So the first loss is trying to get together vectors in the space that would decode into programs that will behave the same. They should be close to each other in the embedding space. So this is really trying to create this locality in the embedding space so that the search is going to be easier later. And there was a question related to this as to Xiaohua after his talk, and this is trying to answer your question. So it's really the idea of getting the behavior. For example, I got this program role here on the left-hand side. I'm going to run in the environment, and then I'm also going to run the program that was reconstructed in the environment. And I'm going to look at the actions taken. And if these two programs, they take the same actions, I don't care if the syntax is different. Like, as long as they're behaving the same, then I want to make sure that the two vectors, they're going to be close to each other in this space, because that's going to help with search later. They have an additional loss, which is also trying to achieve exactly the same thing, but going directly from the vector Z, getting the actions and comparing the actions with whichever actions that the program row executed in the environment. So it's really trying to create a search space that's friendly to search. And then once we learned the space, then we can do local search, very much like how the local search that I described to you before with hill climbing, except it's just called cross-entropy method. So we start with a candidate solution. We have this vector. We're going to apply some noise. We get a bunch of neighbors. We evaluate them in the environment. And then the reward that we get in the environment is going to feed back into the search so that we can decide which vector that we're going to use in order to continue our search from. So it's very, very similar to the hill climbing approach, but now in this hopefully nicer space that we can search over. So this is absolutely nice, very clever idea. I love it. The problem is when we go back And we applied the very simple approach that I described to you before. We have the grammar, and we're sampling from the grammar, and we're doing this hill climbing hill climbing search in the space of the language. And I'm going to call this the syntax space, because we're changing the syntax of the program so that we can get neighbors that way. We can actually do much better than doing the search in the latent space. So here it's just, this is the only empirical results I'm going to show you. On the y-axis, we have return. On the x-axis, we have the number of episodes. And then I'm going to show you 3 methods. So this HC is really hill climbing, and we're doing hill climbing in the syntax space, like I showed you before. And SEBS and SEM, that's going to be the searches that we do in the latent space. So you can see that searching in the syntax space is actually easier than searching in the latent space. There are many reasons why this is happening, and I'll be happy to talk to you about this. I haven't given up in this idea. I still love the idea of leaps, but there's still work to be done so that we can make it happen in practice. And there was a recent paper by McFarlane and Bonnet. Is Matthew here? Maybe Matthew is not here. So Matthew is going to be at the conference. You should totally talk to him about his work. This is the idea of applying something similar to leaps, but supervised learning problems in the ARC challenge. And he has some very interesting results. And I believe that applying this idea of learning latent spaces so that we can do this programmatic search within this space in supervised settings is so much easier. And that's where we should explore first before moving on to reinforcement learning. Okay, that's all I have to say about these results. But I didn't want to throw away like the core idea behind leaps, which is this idea of learning a latent space that can make it easier for us to find policies. And if we can't defeat hill climbing in the syntax space, why not try to combine these 2 ideas? And that's exactly what we're doing. And we call this semantic spaces. So the idea of comparing the actions of 2 programs so that we make sure the 2 vectors are going to be near each other in the space, this has this semantics feeling in the context of reinforcement learning. Because what is the semantics of a program in reinforcement learning? Is really how the agent behaves in the environment. So then now I want to make sure that I can enforce the following idea. If I'm doing my search in this neighborhood space, then I want to make sure that programs that are neighbors, they're going to be semantically different. So whenever I generate a neighbor, I want this neighbor to be different in terms of behavior than my current program. So if you think about it in terms of search, and this is also something that applies to deep reinforcement learning, and I'm not really sure how to use this idea within deep reinforcement learning, but whenever you get a new policy that's a neighbor policy of the current one, you want it to behave differently, because otherwise you're evaluating exactly the same policy as you had before. So then you're just wasting your samples. You're using more samples to evaluate the same policy over and over again. And this happens a lot in the syntax space, the one I described to you before. You change a subtree in the tree and you get a new one, and then in the end of the day, you're going to have exactly the same behavior. So the behavior of the agent is going to be exactly the same. So if I have to draw like a cartoonish version of this space, it's going to look like this. So it's full of plateaus. And we know that this is horrible for local search, because you look around yourself and everybody looks the same. And guess what? They look the same because they behave exactly the current candidate solution. So this is not helpful at all from a search perspective. Just to give you very concrete numbers, 1 out of 5 neighbors will behave exactly the same as a current candidate solution in some of the problems that we looked at in the syntax space. So we want to make it better. We want to make a search space that's more friendly to local search. And this is what we're trying to attain with the semantic space. So we hope that's going to look more like this. So it's very smooth and we know exactly where to go next. And to give you very concrete information, we can go from 1 out of 5 to 1 out of 50 of these neighbors to be identical to the current candidate solution. So then now I know whenever I'm evaluating a program, I know that it behaves differently. So another way of seeing this is that we're using behavior as a proxy for return. It's not going to be exactly the same, but it's a good proxy. If you look at a neighbor and it's going to be identical to the current one, you know that the return is not going to change. But if you can make sure that the neighbors will change in terms of behavior, there's a chance that's also going to change in terms of return. So I think there's something deeper here that we could borrow and use in deep reinforcement learning? Not entirely clear, but maybe there's a research opportunity here. Okay, so how do we make this happen? How do we get a landscape that looks like the one that we have at the bottom? So we do this by using a library of programs. So the idea is actually very simple. We're going to get a MDP, so that's the problem that we're trying to solve. We can see this as a reinforcement learning problem, and a domain-specific language. So this is the language in which we're going to search over. And we're going to try to approximate the underlying semantic space of this language. So we're going to do this by starting with some solution to the problem. So the policy that you see there, it's a program, and it's a program for solving whichever problem that we're interested in solving. And because it has a nice structure like this, you can actually generate with a large language model and get an initial solution to whichever problem you're trying to solve. And once we break down this program, we're going to get a bunch of subprograms like we have there. And the subprograms, they give us behavior of the agents. So if you're familiar with the options framework in reinforcement learning, these subprograms that we're getting, they're essentially options in reinforcement learning. So we're getting a set of options, and we're going to use a set of options, which is forming what we call a library of different behaviors to induce this semantic space. But how do we do this? So let me show you. So here on the right-hand side, we're going to have this little box, and that's our semantic space. So we're still going to use a similar idea to what we did before, where we're getting a tree representing a program, and we're going to change a subtree of this tree so that we can get a new tree. And we're going to get neighbors that way. But instead of randomly generating the subtrees, we're going to use the library that we're constructing here on the left-hand side. So let's say that we have this, maybe this is too small, but the little circle there says N. That's our program N. That's our current candidate solution, and we want to generate neighbors of N. And N is represented by that program that you see on the screen. And maybe it's also too small. I'm going to tell you what's going on. So there is a line at the end of this program N that says C4. It's just calling some function. And what we're going to do is that we're going to generate a neighbor N prime, which is the one at the bottom, where we're just going to replace the C4, a subtree of this program, with a program from the library. Once we do this, we know that we're going into the library and get something that's well-defined. So all the programs that we keep in the library, they have a well-defined behavior. So then we're getting this entire program and we're plugging into this other program. So we're composing a new program through the older programs that we had. So then that way, there's a much higher chance that these two programs are going to have totally different behavior. That's exactly what we're trying to approximate here. Okay, given this new neighborhood function, now we can search over the space given by this neighborhood function, which is approximating the semantic space, with the key idea that we had in mind that neighbor programs, they should behave differently. So, but how do we do this? So we can't just rely on the semantic space all the way. And the reason why is that initially, maybe our library of behaviors would be empty, and then there's no semantic space at all. So we need to mix the search in the old syntax space with the search in the semantic space just to make sure that we can mix these two ideas. Like the search in the syntax space, it's exploring the space of programs so that we can learn new programs and feed them into our library. And then once we have a decent library, we can use it so that we can have shortcuts in the space and that we're trying to mimic this underlying semantic space. So the search is going to be very similar to what we had before. So in this yellow box here at the bottom is just hill climbing. We're going to sample from some initial distribution of candidate solutions. This is, let's say, N. Once we get N, we're going to apply the greedy approach, which is to look at the neighbors and select the best neighbor. So the best neighbor here, it's given by this argmax function. And the neighborhood function that we have in that case is the neighborhood function of the semantic space. And that's going to happen with probability 1 minus epsilon. But with probability epsilon, we're still going to go back to the syntax space and we're going to use the neighborhood function that we had there. So the idea is that whenever we go through the bottom lane, we're exploring the space and learning new programs. Whenever we're going through the upper lane, we're learning to combine existing programs that we had in our library. And then everything else is just hill climbing. We're going to get the result of the argmax operator, and we're going to check, is this a local optimum? If it's not a local optimum, we just continue the search from there. That's exactly what hill climbing does. If it is a local optimum, then we're just going to return this as n star as the result of this search. But we don't stop here. Once we find n star, we're going to use it to feedback and grow our library of different behaviors. So the more we search, the bigger will be the library and the better will be the approximation of the semantic space. This is really cool because the agent is learning how to search as it searches by using this library of different behaviors. Okay. We have very strong empirical evidence showing that the semantic spaces, they are very conducive to search, and it's really borrowing some of the ideas from Leaps. Like Leaps is trying to put together these vectors that will behave similarly, and here we're trying to do something similar. We're trying to find a space that's very smooth and nice, that's going to work nicely with hill climbing. And what we're doing here is essentially give me the next behavior, and give me the next behavior, and so on. Okay. And this is also nice when we have this type of representation, because you cannot ask a large language model, give me the set of weights of a neural network, because I want to start learning to solve this problem. But you can ask, give me a program for solving this. And it actually does a really decent job. And we can make the search so much faster. It's like giving innate abilities to your agent, but just by feeding this library of behaviors with something that a large language model generates. There's lots to be done. And by the way, I'm looking for PhD students interested on these topics. So the idea is to learn how to learn. Like once we have this library of different behaviors, how should we approach a new problem given that I know all this type of behaviors? So how do I search over the semantic spaces that way? All right. So this is the first part. Let me take a look at the second part. I'm just doing the math here to see how much time that I have. Xiaohua, if you could keep an eye and just tell me how, okay. That's wonderful. So now it's going to the second part where maybe you really dislike this idea of doing search in discrete spaces and you don't want to do this at all. And that's fine. I'm actually totally on board sometimes. So I have these two lines of research that we're pushing at the same time. And here, the second line is, what if we try to learn all the programs that we need out of neural networks so that we can learn this end to end? So this is us trying to apply tricks that we learn from software engineering with our agents. So here's it's just a very simple program that ChatGPT generated for me, where we have the sales of 2 stores. And we want to give a discount of 10% if the sales go above some value. And then you could solve this problem by doing the logic twice. Like you're going to get this vector of sales and you're going to do the discount logic. You're going to get the second vector of sales. You're going to do the logic again. But we know that we can do better. We can reuse code, right? I can get, for example, this box here. I can create a function and then I don't have to repeat the same code again. I can just make a function call and I'm going to be done with this. It's a way of reusing the knowledge that we have generated. But how can we do this with neural networks? So I'm going to show you how we can actually break down a neural network. As soon as we see the neural network as a program, we can break it down into smaller programs that are better to generalize across different tasks. And we're going to do this with a very specific architecture. We are working on more general architectures, other architectures, but we're going to be using a feed-forward neural network with piecewise linear functions. So we're going to be using the ReLU activation function. And in this simplified neural network, it just got rid of all the biases just to make it a little bit easier. But in these 2 hidden nodes that we have here, A1 and A2, we're going to be using the ReLU, which is given on the left-hand side. So for each one of these neurons, they can either be inactive if we're sitting on the left-hand side of the graph, or they're going to be active if we're sitting on the right-hand side of the graph. So then, for example, for A1, it's either going to be the linear function of the input x1 and x2, or it's going to be 0. And the same goes for A2. It's going to be a linear function of the input, or it's going to be 0. So now I can look at all possible 4 combinations that I have for these 2 neurons. So for example, if I look at the combination that A1 is going to be the linear function, and A2 is going to be the linear function, now I can rewrite the output H of this neural network as a linear function of x1 and x2. Because a linear function of linear functions is also a linear function. And here's the derivation, just to make sure everybody's on the same page. I'm just going to replace the A1 and A2 with the 2 linear functions. And then we get at the bottom x1 theta prime plus x2 theta double prime. So it's just a way of rewriting for these 2 cases. And I can cover all of them. There are 4 of these cases. I can cover all of them. And then the neural network above is just equivalent to a program with if-then else's. Once we see the neural network that way, what we can do is that we can go inside the neural network and pick little pieces of this program. And maybe not the whole neural network is going to generalize across different tasks, but smaller pieces of the neural network will generalize across different tasks. So that's exactly what we're going to do. So let me just show you a slightly different view. I think it's more intuitive to understand how many of these possible subprograms that we have in a program of a neural network. But before I do so, you should really see the neural network as a really efficient data structure for encoding if-then else's programs. Okay, we call this a structure that allows us to, reason about the number of possible subprograms that we have as neural trees. So it's exactly the same setting that we had before. Now we just have colors because I want to show you this program, this if-then-else program, as a tree. So this is essentially an oblique decision tree. I could say, for example, that the A2 neuron, which is pink, is going to be the root of the tree. And then from the root of the tree, I'm looking at these 2 possibilities. It's either going to be 0, and then I'm going to follow the left branch, or it's going to be the linear function, and I'm going to follow the right branch. And then we're going to rewrite the output of the neural network following these 2 branches based on this decision of either being 0 or being the linear function. But I could also have the blue neuron to be the root of the tree. And then once I do this, I actually get a totally different neural tree. And for example, I could just highlight this one program, and this one program, it's a sub-policy that I could use to solve the reinforcement learning problem that I'm interested in solving. And this is different from that subtree because I changed the root of the tree. Then the question is how many of these that we have? So there's a very intuitive way of how we can discover how many of these programs that we have. If we get the leaf node, that's also a valid policy that we want to look over, and we want to see, is this really a subprogram that we want to give our agent so that the agent can try to solve this problem? So the way to do this is to consider all 3 possibilities for each neuron. So a neuron can be inactive or it can be active. We say that the neuron is inactive whenever we're following the left branch of the tree, let's say for the root of the tree. So if you get this one, you can't really see this. Okay, now you can. So if you get this one here at the top and we follow the left branch, then we're going to say that this neuron is inactive because all the programs that we're going to get on the left-hand side is given that this neuron is inactive. If we follow the right branch, then all the programs that we get on this side will be given that the pink neuron is going to be active. And then finally, there's a third possibility is that the neuron is going to be part of the program. Like, for example, if we get this whole subtree here, which is highlighted, then the blue neuron is part of the program. So for any input X1 and X2, I'm going to ask that neuron, are you active or are you inactive? So given this, we're going to have, if we have n hidden neurons, we're going to have 3 to the n possible subprograms. So now we have a different search space, which we can still search end-to-end with graded descent. This is ongoing research, but we can actually search over the space of 3 to the n with graded descent and find exactly the subprograms that we're looking for so that we can pass it over to the agent to solve downstream tasks. Okay. So let's discuss the effects that you have as you grow your library of different behaviors. So let's say that we're going to learn how to solve a problem. We break down the neural network, and now we have these 3 to the n different programs. Which one should we pick? If we pick too many, then the problem is going to be harder. It's going to be harder because now there are more functions that we need to learn how to use. It's very much like you and me. Whenever we are learning how to use an API, then if the API is very vast, then there are way too many functions that we need to learn. And that's going to make it harder on us. But it's also going to make it easier because you're going to have these very powerful functions that once you learn how to use them, you're going to be able to solve problems more quickly that way. So then the question is, how do we balance these two? And we're going to treat it as a subset selection problem. And we're going to use a loss, which is called the Levin loss. So the Levin loss is something that we actually used in the past to guide tree search algorithms, like A*-like search algorithms. It's called Levin tree search, but here we're going to be using this for selecting a library of different behaviors. So for now, we do evaluate all programs But as I told you, there's a way that we can do this end to end. I'm going to skip the leveling loss slide because of time. But let me just give you the intuition of what we do here. So we have this large number of different subprograms. Which one should we pick? We evaluate the leveling loss for all of them. We pick the one that will minimize the leveling loss the most. And then once we pick that one, we go to the next one, and so on. Eventually, as we grow our library of different behaviors, the leveling loss is going to go up. And that's when we're going to stop. And this set of programs that we have, we're going to pass it over to the agent so the agent can use in order to solve downstream problems. It's essentially giving the agent, here's a bunch of options you can use in reinforcement learning so that hopefully it's going to make it easier for you to solve these problems. So we're going to stop whenever it goes down. So we call this DAC options because we're decomposing neural networks and we're extracting options out of these decomposed neural networks. So the general idea is that we're going to learn how to solve some problems, like the continual learning setting, where once we do, we're going to decompose the neural network. We're going to organize into smaller pieces that are really helpful and reusable across different tasks. And we're going to select a subset of them. And we're going to use these options in downstream tasks. So this helps a lot. Like if the problems you're trying to solve, they're related somehow, you can actually extract structure out of these policies. Let me just show you an example. So this is what we call the combo grid. So it's a grid world like we often do in reinforcement learning, but it's not like any grid world. It's a grid world where if you want to go up, down, left, and right, you actually have to apply a sequence of actions. So for example, if you apply the actions 0, 2, 2, 1, the effect that we're going to have with the agent in the middle of the grid is to go 1 down. And then if you apply all the other actions, then you're going to have the following behavior. The agent's going to go up, up, and then right, down, left, left. So instead of just going up, down, left, and right, it has to apply a sequence of actions so that it makes it happen. And then the question is, can we learn this from data? Can we learn the dynamics of the environment from data? Let me just give you the label so that's easier for you to visualize. So the first 4 actions is going to make the agent go down. The next 4 actions is going to make the agent go up, and so on. So what do we actually learn with this by decomposing the neural network? So for example, we're going to learn that option 3, in this case, it matches exactly down. And we're going to have something similar with other options that we have. Like for example, option 2 is going to go up depending on the state, or it's going to go right depending on the other state. And there's also option 4. It's not quite going down, but it's doing most of the down. So then it's going to make it easier for the agent to solve this problem. Okay. So I'm out of time. So let me just try to summarize this. So if you take this programmatic perspective in reinforcement learning and really taking this step back and seeing the policies as programs, then we can do knowledge retainment. So the idea of creating this library of different behaviors, you're not going to forget it. It's always there. And you can change the library as you learn how to better solve these problems. But you're going to have a library of behaviors that you're going to learn how to use. You can reuse them because you can simply call these functions and use them to solve new problems. Or you can discover new knowledge just by combining them. Remember, this idea, this common thread and everything I'm saying is that we can compose all these policies so that we get something new by composing them. And even if you do not like this idea of having this non-differentiable spaces that we cannot learn end to end. Like if you think about the problem of solving these MDPs, solving the reinforcement learning problem from this programmatic perspective, it's super helpful because you can look at the neural network as a program that you can break down and you can do all sort of cool stuff with it. So thinking of programs might be enough. If you don't like to see the if then else's and so on, or the finite state machines, like it's so insightful to see the policies that way. And okay, so I'm looking for PhD students. Come talk to me if you're interested in some of these topics, but I'll stop here and maybe can I take one question? Should be okay? One question. Gotcha. So the question is the following. So have you looked into combining the search in latent spaces with the search in the actual syntax space? So I haven't done it myself. What we found is that searching in the syntax space is often good enough. What we do need to mix is the search in the semantic space, in the syntax space, because that makes the whole difference. It's really like the exploration-exploitation dilemma. it's happening in the program space. But that's a great point. Maybe there's something here because we can, learn forever how to, we never stop learning, right? You learn some latent space, but as you do the search in the syntax space, you can try to use that information to feedback. I like that idea.
Welcome to the last part of the tutorial. I'm Xingyun Chen from Google DeepMind, and I will talk about neural code generation. In particular, I will discuss those fundamental techniques that really triggers this paradigm shift from building specialist systems for each individual coding application using deep neural networks to building generalist large language model-based code generation systems. So let's get started. Nowadays, we have seen a lot of coding products with powerful large language models as the backbone. So basically here with these LLM-based coding models, we can see that they can help us in various aspects in the software development process. On the slides, I'm showing a demo from Cursor. So basically, given a question from the user, this Cursor system will be able to first explain how it will solve the problem. Then it will suggest some new code snippets and finally make some edits on existing code base. As these models become better and better at solving complex coding and reasoning problems, we are also expecting these models to do more for us. We want them to become reliable developers that can handle software engineering tasks end to end. So for example, from this latest commercial use demo from Anthropic, we can see that this cloud model is able to basically first write some code to create a website, which is required by the user. And then this system is able to control the computer to debug the code and show how the website will look like, and finally save all changes it makes. Recently, people are also developing LLM agents towards accomplish some data science and machine learning tasks. So on the slides, I'm showing this MLE bench data set created by OpenAI, where they show that with the O1 preview model, it is able to win medals in 17% of the cargo competitions in this benchmark. Of course, the current code generation models are still far from perfect. But at least to me, I already think the performance of the latest large language models is pretty magical if we have seen those works way before this LLM happening. So I have been working on the neural code generation field, roughly starting from 2016 to 17. And I'm really seeing this large language model as a game changer for code generation. And it really triggered this paradigm to build right now universal and generalist coding system. So let's look back into 2017, where the first couple of papers on code generation with some execution requirements are coming out. So on the slides, I'm showing this paper, Neuro-Symbolic Program Synthesis, published in ICLR 2017. So in this work, they are handling this flash field benchmark. So for this benchmark, it is basically trying to generate a program in domain-specific language for string transformation. So at that time, from their results, they are showing that they can generate correct code for up to 13 lines. So at that time, generating code beyond 10 to 20 lines has been pretty challenging if you want to guarantee the correctness of the code. So later on, we will really see that large language models are able to significantly improve the complexity of code that can be generated, and also the diversity of coding applications that can be really accomplished for these neural network models. In the rest of my tutorial, I will talk about 3 parts. First, I will talk about the fundamental techniques and background for neural code generation before the era of LLMs. Then I will talk about how large language models are changing the code generation paradigm. Basically, this paradigm shift from building specialist systems to generalist systems. And finally, I will talk about open problems in developing LLM-based coding agents. So let's get started on the first part. So code generation has been a long-standing challenge, and its history can be traced back to 1950s. So on the slides, I'm showing this flash fill task we mentioned before. So actually, this task was introduced in 2011 for Microsoft Excel spreadsheet auto-completion. But at that time, we are using symbolic search instead of using deep neural networks to generate the corresponding code. Similarly, before 2016, the dominant approaches for generating code from natural language is also not using deep learning. Instead, at that time, we are mainly developing methods to learn this explicit alignment between the natural language and the programming language grammar. So such kind of techniques can hardly scale to handle more complicated languages. Then starting from around 2016 to 17, we are showing some neural network architecture coming out for generating code in the flash field domain, as we mentioned before. And also there are some other works on generating programs in more complicated programming languages and also for handling more complex natural language descriptions, such as text-to-SQL generation, as shown on the slides. And in 2021, my work Spreadsheet Coder shows that we can further generate these spreadsheet formulas from ambiguous tabular context in Google Sheets. And this is the system to support the formula prediction feature in Google Sheets nowadays. So from this progress, we can see that learning-based techniques are able to support more complex and ambiguous program specifications in different formats. And this is hard to achieve with pure symbolic approaches, because handling each different type of noise and ambiguity in program specifications requires many different heuristics, and manually tuning all of them requires tons of human effort. So in the context of this tutorial, I will focus on the program synthesis setting. So here for program synthesis, we mean that we want to generate self-contained code given user-specified requirements. So here I will not focus on those auto-completion techniques if there's no clear description on how the generated code should behave, or the generated code itself is not complete in terms of the grammar correctness. So previously, my other cognizers of the tutorial also talk about some other program synthesis applications. So in my part, I will focus on two most commonly used specification formats for software engineering. The first is program synthesis from input-output samples, where given the specified input, the program needs to have the same execution output as the specified output. Another format is generating programs from natural language. So on the slides, I'm showing this application of generating IFTTT programs from natural language commands. Nowadays, this is also a very important application which is related to API calls and tool use. Before LLMs, the standard neural network architecture for program synthesis follows this encoder-decoder framework with the specification encoder and the program decoder. So the encoder architecture can be LSTM, convolutional neural network, graph neural network, etc., depending on different input formats. Then for the program decoder, we can also have the decoder generate programs in different forms. For example, we can have it generate the token sequences, which is also the common practice nowadays with large language models. And if we have a tree decoder, then we can decode the program in its abstract syntax tree format. Or we can even generate the code in the semantic graph format if we use the graph decoder. So to discuss some motivation on principles of the model architecture design back then, let's go into the first case study of this tutorial on text-to-SQL generation. So in a text-to-SQL generation application, the input specification includes a natural language question and the database content. Then the corresponding output should be the SQL query, where if we execute the SQL query on a database, it should return the information required in the natural language question. So before LLMs, typically for text-to-SQL generation models, we will design some specialized encoder to handle some unique challenges in this application. The first challenge is schema linking, where we need to understand the correspondence between the question and different parts of the schema items. So let's take a look at this simple question. Who is enrolled in a bachelor degree program? List the first name, middle name, last name. So from this question, we can see already some examples of how each part of the database content can matter. Specifically, the model needs to understand that the first name, middle name, last name correspond to different table columns. And bachelor degree program corresponds to the database value bachelor in the table degree programs. Another challenge is about understanding the relationship between different tables, especially those linked by the foreign key. So this is important for generating the join clauses in the SQL query. A representative architecture to handle these challenges is called Red SQL. So in their encoder, they design an attention scheme called relation-aware self-attention, where basically they learn some additional embeddings for each type of predefined edges as shown on the slides. So in this way, their self-attention layers are biased towards such kind of tokens with relations. And note that here, the schema linking and also the construction of other types of edges are mostly done via textual matching. So this kind of design is not super robust to typos and synonyms. Then for the decoder, they also design a tree structure decoder based on the SQL grammar and also the table schema. The advantage of this design is that they can guarantee the generated SQL query is executable. Here on the slides, I'm showing the screenshot of the latest leaderboard of this spider text to SQL generation benchmark. We can see that this Red SQL architecture is the backbone of multiple entries between 2020 to 21. In general, this tree structure decoder has been designed for multiple programming languages besides SQL. So on the slides, I'm showing this general purpose hierarchical tree decoding scheme in the sequence to tree architecture. So basically, every time when the model needs to generate a subtree, it will first generate the non-terminal token n, and then the subtree will be generated conditioned on the contextual embedding of this non-terminal token. For those applications where both the input and output are programs, such as for code translation, in our work for tree-to-tree neural network, we show that we can design a model with both tree structured encoder and decoder so that it can better represent the structural correspondence between the input and output programs. And finally, we can also represent the code as a graph by adding some more edges that can represent the syntax and semantic relationship between program nodes. Now let's talk about training and inference techniques. So for training, I will talk about supervised learning with synthetic data and reinforcement learning from syntax and execution feedback. Then for inference time techniques, I will talk about execution guided synthesis, code re-ranking, and debugging in the synthesis loop. So clearly this is not an exhaustive list of possible ideas, but these are representative directions to show a common principle to boost code generation performance, which is to leverage code syntax and execution as powerful signals. So let's get started from the training part. For program by examples applications, designing synthetic data has been a common practice actually. So recall that in a program by examples task, the model input includes input-output pairs, and the model output is the program. Then for synthetic data generation, basically we switch the order of how each part of the program will be generated. So basically we first have a random input generator to sample those possible inputs in a predefined space. Like in the flash field domain, this will be some random strings. Then we will have a random program generator to sample programs in the programming grammar space. Then given these randomly generated inputs and the program, we will then execute the program to obtain the output. This process guarantees that these generated input-output pairs and the programs are verifiably correct. And finally, we can have another filtering procedure to further control the data quality. For example, to do some deduplication and removing trivial programs. Generating synthetic data for text-to-code generation is much harder back then due to the complexity of natural language grammar. So in 2015, there's a paper called Building a Semantic Processor Overnight, which introduces this procedure to generate text-to-code paired data in some kind of domain-specific language. So the idea is that we will first generate synthetic text and code data based on some predefined translation grammars between natural language and code. Then there's a crowdsourcing stage to paraphrase the synthetic questions so that they can look more natural and diverse. From this generation process, we can see a clear limitation. Because such kind of process relies on these manually designed alignment rules between natural language and code. So this inherently limits the complexity of grammars that can be handled. Now let's talk about reinforcement learning from syntax and execution feedback. So the motivation of using reinforcement learning has been also greatly covered in the previous part of the tutorial. So here I will talk more about these software engineering applications. So in many cases, the correct code to solve a problem might not be unique due to this diversity of the syntax. And also in many cases, if we only care about the final execution, there can be different details in the algorithmic implementation. So if we only do supervised learning, then it might only penalize those alternative programs that can also be accurate. But with RL, it will encourage the model to explore those alternative paths. So since the algorithm part has been covered by the previous tutorial speakers, so I will just list some example rewards we can use for these software engineering applications. So for example, on the slides, I'm showing one example design. If we have unit test as the feedback, we can design different positive and negative rewards based on whether the code already passed all the unit tests or only passed a subset of unit tests or have any kind of runtime errors. So now we will talk about inference time techniques, starting from execution-guided synthesis. In the previous part of the tutorial, other speakers have talked about this Carol domain. So here I would also discuss the second case study of generating programs in Carol. But here we will see how these different inference time techniques can be connected to jointly boost the performance. So recall that in a Carol domain, we are trying to generate a program to control a robot in a 2D grid world, so it can basically transform the input state into the output state. So in the standard encoder-decoder architecture for input-output program synthesis, at each generation step, the input to the model will be these separate embedding vectors for these each individual input-output pair. Then the decoder will sequentially generate the program. So if we look deeper into this process, one limitation of this encoder design is that we always feed in the initial input pairs into the model at each decoding step. So we are not actually really leveraging these some properties of code execution here. So what do I mean here? So basically, if we think about a program as a series of program statements, then actually after each statement, it tries to transform the execution state from the previous step to the next step. Actually, when we as humans are writing code, we are implicitly or explicitly thinking about how this program will execute line by line or block by block. We are usually not just writing the whole program end to end without thinking about such kind of semantic meaning in the meantime. So basically, based on this intuition, in our work, we designed this execution-guided neural program synthesis. And I will first use an example of generating straight-line programs to illustrate this idea. So which means that here, the program is pretty simple. It doesn't have complicated control flow constructs such as loops and conditionals. So at the beginning, the input to the model includes the initial input pairs as the current state and the target state. But with execution-guided synthesis, every time when the model predicts a program statement, such as put marker here, this statement will be immediately executed and result in a new state. So at the next time step, we can see that this current state is changed into this intermediate execution state. So this new state will guide the subsequent synthesis of the program. In this way, the model is really able to leverage these intermediate execution results, which explicitly tells the model how close the current state is to the target state. So this will be very helpful for the model to actually plan for the subsequent generation of the program. We can further extend this framework to generate programs with branches. So every time when the model predicts an if statement, we know that this if statement will have two branches, one for true and one for false. So in the standard framework, basically for both branches, we will feed all the improper examples into the model for generating the program. But intuitively, the true branch only depends on those inputs that satisfy the constraint, and the false branch depends on the rest. So in execution-guided synthesis, every time when the model predicts an if condition, we will first evaluate all the inputs on this condition and split it into two subsets, one for true and one for false branch. Then we generate the corresponding branches using the subset of the improper examples, and finally we'll combine the two branches together. So in this way, we can better utilize this program semantic meaning to guide the synthesis process. But there are also some programming languages, or there are some scenarios where this program interpreter is not available to explicitly give us these intermediate execution states. So in our follow-up work, we propose this latent executor framework where we train a neural network to approximate these intermediate execution states. So basically for this latent executor, given the execution state at the previous time step and the currently generated program, then this latent executor will predict the next execution state. The main challenge of training this latent executor is that there's no direct supervision on these intermediate execution states. And this is precisely the reason why we want to train this latent executor at the first place. However, at least we always have the training target for the last time step, which is the full program output. So the idea to train this module is to basically construct a corpus with both short and long programs. And we hope the model can learn these intermediate execution states in long programs by learning the execution results of short and complete programs. And because this program execution corpus can be synthetically generated at scale, as we also mentioned before, so basically this allows us to flexibly control the length distribution of the corpus. In our evaluation, we show that basically by modeling the program execution, we can see a performance improvement on both the carrot domain, where we can have this interpreter to give us intermediate execution states. And we can also show this improvement on another domain of generating C programs for list processing, where there's no interpreter available. Previously, we have shown that we can use this execution when we are generating the programs. In fact, we can also utilize execution once we generate the complete program, especially if we are allowed to generate multiple programs at once, and also to select final candidate from not just one program. So basically, in the execution-guided synthesis work, we also design this execution-guided ensemble. So basically, let's say if we train multiple models and they produce different programs, we will first execute all of them on the given improper examples in the task, and we will see whether they at least pass those given improper pairs. So for those that already fail, they will not be considered in the second stage of program selection. But in a typical program by example task, usually there will also be some hidden tests, so that this means that even if the model passed those given improper pairs, it might still fail the final test. So for the remaining programs that pass these improper examples in the problem description, we will, in this work, we use some pretty simple ensemble principles, including selecting the shortest predicted program, or selecting majority voting, which is the most frequently predicted code based on exact match. So for carrot domain, it is feasible because the grammar is relatively simplified. But later on in the second part, when we talk about LLMs, we will talk about some more advanced techniques to do this code re-ranking to handle more like complicated general purpose languages such as Python and C++. So if we put everything together, we can see that on all the different kind of synthesizers we use, these like ensemble techniques will always boost the performance, especially if we compare it with the one without using execution. So last, I will talk about this process of debugging in a synthesis loop. So this might look like more like related to the current agentic workflow. So basically, this is a work we have done in 2020. The idea is that after we have a synthesizer generate a program, we will train another neural network as the debugger to propose some more edits on top of the synthesizer output. So for example, here I'm showing a very simple example as editing trace. Basically, on top of each token, this debugger will decide whether we want to keep the current token or insert some more program statements or delete the current one. So at that time, we are training another separate debugger in 2 stages. So in the first stage, we will train a model on synthetic data with pairs of programmatically corrupted code and with their corresponding correct code. So in this way, we can again generate this data at scale. And in the second stage, we will train a model on those like real wrongly predicted code by the synthesizer model with the corresponding correct code. So in this way, we can also co-train the synthesizer and debugger. For evaluation, we can see that also on top of different synthesizers, we can see the improvement with the debugger. Actually, we are showing that we can train just one single debugger that can help for multiple different synthesizers. So to summarize, in the first part, I will show that compared to rule-based systems, neural code generation techniques support more ambiguous program specifications in more diverse formats. However, there are still some weaknesses of these neural code generation models before LLMs. First, it requires separate training and architectural design for different programming languages. And also, the complexity of correctly generated code is still limited. On the other hand, later on, we will already see that most fundamental techniques for neural code generation I discussed here remain important before and after the LLMs, and especially this common principle of leveraging code syntax and execution to design rich feedback signals. So now let's move on to discuss the second part on how LLMs are changing the code generation paradigm. So the most significant change after LLMs is that we no longer pay a lot of attention in designing different architectures for different coding applications. Instead, we are training a unified generative model for different modalities, and especially there are a lot of shared training recipes between text and code. So basically, these latest LLMs are considering a programming language just as another natural language. And these works are showing that if we have a large scale like training with a lot of data and also a large scale off-the-shelf model architecture, which is nowadays mostly based on a transformer, then it will give us high-performance generative model for both text and code. The first success to illustrate this LLM paradigm is basically this OpenAI Codex model. So if we look at this demo again, probably it will look less surprising right now. But at that time, when the demo first comes out, it was very impressive because if we look at the natural language instructions shown on the slides, it is pretty complicated with a lot of implementation details. But once the model is given this natural language instruction, the model is able to immediately generate the code without any errors. And after we execute the code, it just gives what we want. So this is definitely a much harder task, especially in terms of this complexity of the input specification part if we compare it with the previous text-to-code academia benchmarks. Again, same as the text domain, we are seeing the scaling curves of this coding performance with respect to model size. So here I'm showing these scaling curves with both the OpenAI Codex model and also the Google PaLM model. So we can see that in different model families, if we scale out the model architecture, usually we will see this accuracy increases for across different benchmarks. So in the part about LLMs, I will focus more on the training and inference techniques. So for training, again, I will talk about supervised learning with synthetic data. But this time, this synthetic data is no longer programmatically generated. They are generated by LLMs. And I will talk about reinforcement learning with execution feedback. But this time, we will see that besides those scalar rewards, we will also incorporate this like natural language information as part of the feedback loop to guide the model for generating code in the data terms. Then for inference time techniques, I will talk about code re-ranking, debugging in a synthesis loop, and also I will talk about agentic workflow that really puts all the components together. So if we think about these techniques, still they are leveraging the code syntax and semantic information as we discussed in the first part. But with LLMs, we are further showing that we can leverage this natural language understanding and instruction following abilities of these latest foundation models to further boost code generation performance. So let's get started with the first part. So for synthetic data generation, again, I will talk about two typical use cases. The first case is to generate code in this like a setting of machine verifiable synthesis problems. So on the slides, I'm showing this diagram from a paper called Language Models Can Teach Themselves to Program Better. So in this work, they are considering this programming puzzle problem. So in each example, this F program is the puzzle, which is a function that actually shows the specification. So if we look at these examples, especially the second one in the bottom, actually it shares some similarities to the improv examples we discussed before. Basically, it very explicitly shows what is the intended execution behavior. Then this G function is the intended corresponding solution. The main difference between this process and the previous process for generating synthetic data for input-output program synthesis is that this time, both this specification function and the corresponding program solution are generated by LLMs. For example, these specific functions can be generated via few-shot prompting. And again, because of this setup, we can fully verify the correctness of each problem generated in this process. The major breakthrough of synthetic data generation with LLMs really happens in the space of text-to-code generation. So on the slides, I'm showing this diagram from the Magic Coder paper, which was used to construct this OSS instruct data. So basically here, this work is showing that we can prompt the LLM to generate natural language coding problems and their corresponding solutions. And there are a couple of different ways to improve data quality with LLMs in this space. For example, in this OSS instruct data generation, they are conditioned on this data generation from some external corpus. So in this way, they can kind of control what is the current prompt trying to solve in terms of the coding applications and what kind of code should be generated as the target. And in some other works, such as in the Llama 3 paper, we can also basically prompt the LLM to generate corresponding unit tests for data filtering. And clearly, because these LLM-generated unit tests are still imperfect, so compared to the previous machine verifiable program synthesis setting, the data generated in this process will still have some noise. So the quality really depends on the capability of the LLMs. But at least compared to the earlier setting before LLMs using this grammar sampling, this process allows us to obtain much more diverse data, and also the data complexity itself can be greatly boosted. Then let's talk about reinforcement learning from execution feedback in natural language. So on the slides, I'm showing an example of the RLEF paper from Meta. So the idea here is that when the model is trying to generate the program, besides the final reward that telling the model whether it passes the unit test or not, since we are already using the executor in the loop, we will also incorporate those execution feedback in natural language in this generation process. Like here, for example, when the code fails the unit test, we can store in this information summarizing which unit test is failing. Then basically this execution feedback will be part of a prompt in the next turn of code generation. And if we train the model in this way, it can not only improve the model in its program generation process, it will also help the model be better at debugging. So if their evaluation, they basically try this approach on different benchmarks with different scales of Llama 3 model. And they show that RLEF consistently improves the performance. And also, this improvement will be more significant in the multi-turn setting than the single-turn setting, because then the model can fully leverage its ability to do this multi-turn debugging. Now let's talk about inference time techniques. To start from code re-ranking, we will go into the third case study of this tutorial, which is about generating competitive programming solutions with the AlphaCode system. So basically, in the AlphaCode work from DeepMind, we are considering this competitive programming setting, where in the problem we have very long and complicated text description, which was designed to fool the best human programmers. And also, we have input-output examples, as usual. So with the latest AlphaCode 2 technical report, which is based on a Gemini 1.0 Pro model, this system was able to rank top 15% in online Codeforces coding contests. So compared to the latest model we have, this model itself is no longer the best one, but still this system can achieve pretty good performance when we have very advanced inference techniques building on top of the model. So now I'm showing this AlphaCode framework. This is the framework we used to publish our first version of AlphaCode paper, which was the cover of Science in 2021. So in the training process at that time, we still train a smaller model with specialized GitHub data pre-training, for example, which can be nowadays replaced with some more powerful large language models. But for the inference time techniques, it is still very important for the performance. So basically, in the tutorial, I will focus on this inference time technique of filtering and clustering, which basically shows that we can leverage code execution for re-ranking. So the first stage of filtering is pretty much similar to the first stage of execution guided ensemble we discussed before. So we want to basically execute all the generative programs on input-output examples given in the problem description, and we filter out those programs that fail. For competitive programming problems, in many cases, the generative programs can already fail on these given input-output examples. So this filtering procedure is very important. The main new thing here is about how we will select the program from the remaining solutions that can pass the visible input-output examples. Recall that the main challenge here is that for test problems, we do not know those final test suite that is behind the evaluation system. So in the AlphaCode work, we are thinking about it from a different perspective. So since there are no tests here, why don't we just generate the test by ourselves? So basically in the AlphaCode work, we train a separate model to generate these new test inputs given the problem description. And since we have a training problem corpus, then we can train another model on top of it. Then we will execute all these generative programs on these generative inputs. Then we will cluster those programs with the same outputs together. So this is assuming that if this test generation model is good, then it will generate representative examples to cover the possible execution space. So for those programs with the same outputs, they should be semantically equivalent, ideally. Then we will sample one program from each of the 10 largest clusters. So in our final evaluation, we will send these top 10 programs for the full test. Then on the slides, I'm showing these ablation studies to show this effect of filtering and clustering. If we compare this red curve to other curves, we can see that filtering with execution is crucial because, as we mentioned before, in many cases, these programs cannot even pass the given input-output examples. Then if we compare the other curves, and especially if we compare the bottom table to which shows the improvement from scaling the model from 9 billion to 41 billion versus with 41 billion model, we add the clustering procedure. We can see that actually here, this clustering process can provide more performance gain than simply scaling out the model sites. So this also shows another evidence of scaling the inference time techniques, which can be helpful in many cases in addition to scaling up the model itself. But if we compare it with the Oracle sample selection, the blue curve, clearly there is still a gap. So in the AlphaCode work, we are trying to train another model for this text generation. But in this LLM age, we can also try to have the single large language model to both generate the code and generate unit tests. So we just need to design different prompting scheme to do so. So basically on the slides, I'm showing this framework from the Code T paper, where they are trying to prompt the LLM to generate unit tests. Then they will measure this execution agreement between the generated code and unit tests for re-ranking. So clearly here, this re-ranking performance will be heavily depend on the quality of the generated unit tests, which also depends on the complexity of the task and also how strong the underlying model is. In the final case study of this tutorial, I will talk about this debugging in a synthesis loop. So I will introduce our work self-debugging. So this time we will no longer need to train another debugger model. Instead, we will achieve this debugging procedure via the prompting with a single LLM. So basically in our for loop, in each step, we will first generate the code, and then we will execute the code, which this executor will give us some feedback on the unit test or whether there are some runtime errors. Then with this execution and the code, we will also prompt the LLM to generate some explanations in natural language about what the code is trying to do and also what the execution results are telling us. Then with all these feedback messages, the model itself also needs to make a decision of whether the code generated now is accurate. If so, this debugging process will terminate. Otherwise, all these feedback messages will be put into the next term to generate new code. So in this self-debugging work, we study different types of feedback formats depending on what we have from the problem, and also in many cases based on human intuition on how we can improve our debugging efficiency. So in the simplest feedback, we are basically having this a short universal information for all the wrong code, saying that the code is wrong, please fix it. Then for unit test feedback, we will include these execution results as part of the model input for the subsequent terms. And then for code explanation, we will prompt the model to generate a line-by-line explanation of the current implementation. This is inspired by the robot duck debugging process for humans, where by explaining the code to ourselves, we will know better at what the code is doing, and it will help us find those subtle implementation errors. And finally, we design this trace feedback. The idea is that we can also prompt the LLM to simulate this line-by-line execution and produce an execution trace by itself. So because this trace is generated by the model, again, it might have some errors, especially when it is simulating these intermediate execution states. So basically, the idea here is kind of related to the latent executor in the first part. But again, the advantage of this design is that this trace feedback can be general across different programming languages, and also it can utilize this natural language understanding ability of the model, so that the model can probably better understand this execution information summarized in a natural language format. So for iteration, we basically conduct this debugging process on different benchmarks with different models as a backbone. So we can see that this self-debugging process consistently boosts the performance across different LLMs on the Spider task for text-to-SQL generation, transcoder task for Python and C++ translation, and MPPP, which is an earlier text-to-Python generation benchmark. And we can see that more informative feedback can further improve the debugging performance. So up to now, actually, we have covered the most basic components for building a general purpose LLM coding agent. So the slides, I'm showing an example framework from the Codec paper. And there are also some other frameworks discussed in other papers and also right now in different coding products there. So in general, there are a couple core components that are important for building an effective coding agent. So first, we need a model to be able to do multi-term generation with execution feedback, which has been discussed in the previous part of the tutorial. And we need a model to be able to do reasoning and planning to perform each action. So this will be also heavily depending on the capability of the fundamental model. And finally, there are also some works that can be done to improve this agent environment interface. So by default, the principle is that if you can give more information to the model, it will be always helpful. But there are also some other interesting design choices. And due to the time limit, I will not go into the details here, but I list some references here, and you can take a look if you are interested. Another idea is to design this multi-agent code generation framework, which is also be more inspired by this human coding practice of collaboration between different team members. So basically, we can have multiple LLM agents to play with different roles. On the slides, I'm showing this framework from the agent coder paper. Basically, there are different components as programmer, test designer, code reviewer, etc. So earlier, basically in the debugger, in the synthesizer loop, we are showing that we need to train different models to play different roles. But actually with LLMs, again, we can just have different prompting schemes for role playing on top of the same backbone of LLMs. So to summarize, in the second part, I show that the trend after LLMs is to build this unified generative model for different modalities. So basically, at this time, the code format is usually blended with other modalities, such as text and image. And we usually want to have one model for multiple applications, like a single model can do code generation, editing, debugging, question answering, etc. So one advantage of this LLM-based code generation paradigm is that it enables quick adaptations to new tasks via prompting. So we don't need to retrain one model for each feature we want. And this support of multi-term free-form natural language conversations also provides a more interactive user experience, which is right now basically the foundation we are realizing to use to build these coding agents. So finally, I will discuss some open problems in developing LLM-based coding agents. So the first thing is definitely about the performance gap between clean evaluation and real-world applications. So this is also the reason why right now people still have kind of conflicting ideas of whether the current coding models are really working or not. So for example, in the left figure, I'm showing these results from the latest OpenAI O1 block. So they are showing that with the O1 model, it is able to beat 90% of the human programmers on Codeforces contests. The concrete number doesn't really matter here, but the idea is that this SOTA model can perform pretty good in the competitive programming setting. And this is actually a very hard task for most humans. On the other hand, if we look at their performance on some other benchmarks for solving common software engineering tasks, like resolving GitHub issues in the Sui bench, right now the best accuracy is still below 60%. While for most of human programmers, if we are patient enough and spend enough time, we might be able to solve nearly all of them. So there's still a gap here between actually the algorithmic difficulty of the model can deal with versus actually how well the model can conduct these multi-turn actions to perform each stage in the full software engineering workflow. And that is for different applications. But even if we consider the same application, we can still see a big gap between different setups. So here on the slides, I'm showing the second version of the Spider benchmark. So in the previous part of my talk, I'm mainly talking about the first version of Spider dataset. So if you remember the previous part, you will see that actually the setup is much cleaner. There seems to be a pretty explicit syntax alignment between the question and actually the table schema. But basically, the second version of this leaderboard, they are showing that if you make it be more similar to the enterprise cases, where basically you need some external knowledge or documents to see the alignment between the database and questions. And basically, this process will be less self-contained in a single prompt. You really need the coding agent to be able to do this multi-term generation. Now, actually, all the SOTA models are not doing very well on this second version of a benchmark. And especially, for example, this OR model is able to only solve 17% of the task in this benchmark. Another concerning factor here is about the safety. So on the slides, I'm showing one benchmark called red code. So the idea is that if we ask this coding agent to execute risky code, which will be part of their task, actually the current coding agents will have very low rejection rates. So basically, there are two factors here. One is that the model probably still has some limited understanding of code semantic meaning, so it doesn't know whether the current code is risky or not. The second factor might just be that the model is still ignoring some safety factors that it should consider while it is following users' instructions. So basically, in general, for the neural code generation, especially right now in this era of LLMs, there are a couple open problems that we need to consider. The first is about long context understanding. This is very critical for code generation because in the end, we want this agent to really work on the entire repository we are working on. It is very different from the standard solving some standard STEM problems where the question itself can be very self-contained. A related challenge is about retrieval augmented generation. So since the corpus is too large, in many cases, we cannot throw in everything as part of the model input. Then how we can design some system so that the model can understand which part of the code it should look at. So basically, this will be very important, especially to enable this multi-file editing. And long-term reasoning and planning is crucial for building these coding agents because as we see before, to really solve a software engineering task end-to-end, the model cannot just generate the code in one shot. It includes a very complete loop. For example, it needs to know how to debug. It needs to know how to design the unit test. It needs to review all kind of perspectives on the code to concern about some safety factors. Or sometimes it also needs to retrieve related documents for the subsequent generation. So all of these really require this long-term and coherent planning. And this is still something the current models should be improving. And about code semantics understanding, so a lot of the safety issues we can see here is about the model might still have some limited understanding of the code execution behavior. So this is why in many cases the generated code will still kind of missing some corner cases. This is also the reason why some people are concerning that people will rely on the current LLMs too much, because in many cases, this LLM generated code looks pretty good in many cases, but it still misses those corner cases badly. Then it's about code verification. So in the old age before LLMs, and we will see that in many of the code generation design, they are trying to make sure that the code is valid once it is generated, because there are a lot of controlling factors in the architecture and decoding algorithms. But in LLM space, if something coming out of LLM itself, it will be harder to verify these features. So basically, for the future work, another factor to think about is how to also improve the user trust by incorporating some more verification procedure into this code generation algorithm, especially those empowered by LLMs. And finally, safety is definitely a concern. Because in many cases, if the model solves your like math problem like wrongly, you will just feel very disappointed. But if the model accidentally generates some bad code and injects some virus in your system, then this is not what you want. So this is the reason why right now, even with the computer use capability, probably you still want to watch the model while it is accomplishing the task. You might not want it to just freely handle your computer and do something you don't really want to see. So this is the end of the tutorial. Thanks everyone for being here and listening. And right now we can open up for questions.
I have a question. You talked about the evolution of the code generation. And if I understand correctly, the paradigm shift to LLM coders, it is completely changed the whole field. And the question is, what we can learn from all past experience that you talked about, like before 2022 or 2023, or it's all obsolete?
Yeah, thanks for the question. So basically, I think the main change here is the mindset about how to basically baking these like code specific features into the model. So in the past, mostly people are thinking about the architecture change, which basically will be like more specific to each individual programming language. But in the age of LLMs, people will think more about this like scaling and data and training techniques. So for example, in the second part, I've been talking about how we can incorporate these different feedback in natural language format or other format in the training procedure for allowing the model to perform this like multi-term code generation and editing, etc. So I think the common thing of utilizing more of coding-based features will still be very important here. It's more about like which part we should add such kind of heuristics and what are the techniques that can really scale up that can like hold for multiple modalities. So that is the important one going forward in the current age of foundation models.
Hi, my name is John. I have a question on like what do you think contributes to the difference between everyday coding question and the competitive level coding question? You can see there's a gap in the performance that state of our model are performing really well in competitive level coding question. But if you look at like Sweetbench, the state of art models are still pretty mediocre at this point.
Yeah, thanks for the question. So for here, like there are a couple of factors. The first is about like this like agentic task versus more of like single term like self-contained problems. Because for competitive programming, it is a very clean setup. Your problem description needs to be self-contained because there's like no way you will get some further like feedback in the online context environment. And also there are a lot of like unit tests which can be very clear on what we want. But in those like cases of resolving the real like GitHub issues, it is a multi-term process. So even for the simplest task of like fixing some bugs, usually you need the agent to like download the repo. It needs to install the related packages and debug it when there is some unintended issues. And basically this is a back and forth process. So for the existing coding models, I would say that they are getting better and better. And in many cases, there are still some consistency issues if it needs to perform these like multi-term actions. So this is the reason. And especially for this competitive programming, like including AlphaCode and other systems, we are usually fine-tuning the model on previous competitive programming problems. And because I personally did competitive programming myself when I was young. So the idea is that if you practice enough on problems of the previous years, there are some high-level similarities. So if your model is good, then it will know kind of these combinations of different algorithms. But for the real world software engineering task, it is more diverse, although it might not be that complicated in terms of the reasoning part.